Hi, I'm Dave Hodson from CIMIT. I'm going to give a brief overview of the current Rust situation and also look a little bit at the historical background to the Rust surveillance work. So when I thought about this talk, I looked back at the presentation I gave at the first BGRI technical meeting. This was in Obregon in March 2009. So I thought it'd be a good idea just to look at how we were thinking then and how things have evolved over time. So obviously UG99 was the key focus. We'd had the sound in the alarm. We'd seen the formation of the Buller Global Rust Initiative. And we'd also got a clear need for effective monitoring and surveillance of rusts. We had an outline of the how we'd like the system to work, and this was very much based on the FAO Desert Locust system. So we saw we needed georeference data inputs, we needed a spatial database that could handle everything, needed to be able to do some analysis, but we also needed a set of tools that we could have as outputs for access to information, so maps and charts and graphs and reports. We'd also put together some standardized survey protocols and started in-country training with partners. We were beginning to get some data into the system. So I think at that point, we just got over 1,000 records into a database. We'd also started to look at the influence of winds and rainfall patterns on the movement of the pathogen. So you see here the use of early wind models indicating movement from Yemen up towards Iran. So we were thinking at this time that other variants of the pathogen would likely move in a similar direction. In terms of our future activities at that time, we obviously wanted to expand the surveillance network, more efficient data flows, improved data layers. Obviously, integrating race analysis data was a key one. Access to information, but also to be able to include other rusts as well. So if we fast forward to the current time, we're now looking at having one of the world's largest operational crop disease monitoring systems. So we've got about just over 39,000 georeference survey records in the database now, and around maybe 9,500 rust isolates records. So I mean, this is a fantastic effort, and a huge number of partners have contributed to this. Just to illustrate this in the form of maps, so this is where we stood around 2005 in terms of surveys, and this is showing where we are currently. So getting really good coverage, certainly across most of the developing country wheat growing areas, and a really great resource to have. Also, thanks to colleagues in Denmark at Aarhus University Global Rust Reference Center, we've been able to put together a state-of-the-art data management system, the Wheat Rust Toolbox. We can get information into the system easily. We can do quality control, and we've got a whole range of tool outputs, interactive maps, graphs, and charts. So this system, it's now holding, say, 39,000 records, and it's a great resource. Also critical has been the network of the Rust pathotyping labs. So fantastic support from the international labs, so USDA Cereals Disease Lab, AAFC Lab in Canada, Global Rust Reference Center in Denmark, and then more recently the Turkey ICARDA Regional Rust Research Center based in Izmir. But also I think to note the country labs and labs like AMBO in Ethiopia, now the capacity's there, up and running, doing great stem rust race analysis work. As we speak, together with colleagues in Calro in Kenya, a new greenhouse is just being built at Njoro. So I think within a year we should have another great facility up and running in East Africa. Thanks to the efforts from those labs, we've been able to track the pathogen. The example here is for UG99. So this is what's happened over time with the monitoring. So we're now looking at a situation where we've got 14 confirmed races, and those are spread across 13 countries. So the pathogen, it's managed to acquire increased virulence over time, and it's also spread over large distances. Although UG99 is obviously still a threat, then there are other global stem rust threats that have now emerged, which we're monitoring, and we see them as a serious threat. So this graphic just illustrates some of the recent appearances of stem rust. You can see it's distributed over many countries, many regions, and these are all non-UG99 races. Thanks to the work of Les Sabo at the Cereals Disease Lab in Minnesota, the genotyping work that Les's group has done has really given us a clear picture of the population structure from all the sampling that's been done. So we've obviously got, there's the UG99 clade. It's very distinct out on its own. But I flagged a couple of other clades, this clade 3 clade and this clade 4. These are ones that are currently a source of concern, and we're seeing important new races in these clades. Just to try and illustrate this and flag some of the recent events, we're seeing large-scale outbreaks of stem rust in many different places. And all of these have been caused by non-UG99 races. In Sicily, we saw 20,000 hectares, and probably in a subsequent season, more like 50,000 hectares affected. This was a clade 3 race that was behind this. Similarly, Ethiopia, we saw a large epidemic, 2013, 50,000 hectares affected again. This was a clade 4 race that was behind that outbreak. In Western Siberia, Kazakhstan, we've seen an estimate of probably around 3 million hectares affected by stem rust. And in this area, we've clearly got, it's a sexual recombining population. Similarly, we've seen the same occur in Sweden. So again, very high race diversity. And also now in Georgia, we're seeing the same thing. It's very strong indications we've got sexual populations, and these are the source of new race diversity. A couple of examples of the new races that are coming up. This TTRTF, so this is the one behind the outbreaks on Sicily. It was picked up in Georgia in 2014, and you can see the spread over time. It's gone into Europe, the Mediterranean basin, into the Middle East, but also migrated down into Africa. You can see some of the key virulences associated with this race. Another one is TKK-TTF. So this, I think, was first, again, 2014, I think Iraq or Georgia were the first records. But again, you see the spread across Europe, across the Middle East, down into East Africa. And this one is likely to be, I think, the dominant race in Ethiopia, probably in the next season. It's really increasing very rapidly and affecting many varieties. For yellow rust, we've got far more information on yellow rust, and really thanks to colleagues at the Global Rust Reference Center in Denmark, but also the Turkey ICARDA lab in Izmir, generating really good information now on yellow rust. I mean, this just gives an overview of how mobile the yellow rust races are, and the spread. Basically, it's global spread, and this trend seems to be increasing over time. few recent examples with yellow rust. So this PSTS11, it was picked up in Afghanistan in 2012. By 2016, it had moved into East Africa and causing large outbreaks and spreading throughout that region. It's also recently been picked up in Turkey. Similarly, PST13, PST14, they were picked up Europe, North Africa. They very quickly moved to South America, where they caused the largest epidemics in 30 years. Worryingly, there's been a new genotype, new race picked up in Egypt in 2018. This was also now being picked up in Turkey. This one's affecting both durum and bread wheat. So I think this is another one that we need to be watching out for in the future. In addition, thanks to links to University of Cambridge and the UK Met Office, they've been able to develop advanced forecast models looking at dispersal, but also environmental suitability. So these have really given us whole new indication on migration routes, and also now have opened the door for in-season early warning systems. So in Ethiopia, we've put together an operational early warning system. So we've now got near real-time detection in the field. So we're using apps on mobile phones for surveys. We're also doing crowd sourcing using phone surveys to extension agents. We've been able to automatically harvest the data straight into the forecast model pipeline that's been run by Cambridge UK Met Office, and every day getting a 7-day forecast of dispersal and also risk. Information's going out to partners in weekly advisories, but we also have the ability to send out targeted SMS alerts. And this system we're now reaching, it's in the hundreds of thousands of smallholders. And it's timely and it's actionable information. So the feedback that's coming is that there's the possibility to get control ahead of the disease in key areas, which is a major breakthrough. We're also now being able to transfer that technology across to South Asia. So we've got some initial work running in Nepal and Bangladesh. You see some promising initial outputs. So this was the model forecast early February, large deposition of stripe rust spores coming in from sources in northwest India, and then subsequent occurrence of the disease corresponding to those areas. But this was late March. So you've obviously got a time window where farmers can take some control measures. Also linking with Diane Saunders' group at the John Innes Centre in the UK, come up with new pathogen diagnostic systems. So this system, it's based around nanopore sequencing. And it's a real, I think, a quantum leap forward. So we can go from a field sample all the way through to getting an identification down to genetic group in just two days. So we've got this running for yellow rust, and now starting to expand it out in Ethiopia. And the information here we can feed straight into the early warning systems, so hopefully get prioritized control of any new incursions in the country. So I think this is exciting. We're looking to try and expand this to other regions as well. Other new technologies, we're also starting to look at use of drones, satellite imagery, and also artificial intelligence, machine learning. So these, I think, could potentially play an important role in the future. In terms of next steps, we've been very fortunate. We've just got a new 5-year project that's been funded by Gates Foundation, the UK aid, USAID, and also the Foundation for Food and Agriculture Research. So this is accelerating genetic gains in maize and wheat for improved livelihoods. And one of the primary objectives is around rust surveillance. So this will allow us to continue with the surveys, the race analysis, but also to keep building the capacity in East Africa. There's also several other, I think, relevant additional projects. So these are very much around the forecasting, early warning systems, and also the diagnostics. So I put a list of these projects that we're involved with. And I think these are really building on the surveillance and race analysis work. But I think we're clearly looking at a point where we need to be developing long-term sustainability plans for the rust surveillance. I mean, we've been, had incredible support from donors in different projects for over a decade now. But I think we're now looking at the point that we have to move beyond solely project funding and try and find a way to have these sort of systems running sustainability and for the long term. So just to wrap things up, I mean, clearly wheat rusts are incredibly damaging, and they're very important basically wherever wheat is grown. And we're really seeing an increasing number of threats. I think a lot of the original vision we had for the global rust monitoring system is now being realized. I think we've made some great progress. I mean, thanks to all the contributing partners. I mean, we've put together this very comprehensive operational monitoring system, and it really stands out as being quite unique. We've also been able to develop the operational early warning systems. So we've got things up and running in Ethiopia, but now expanding that out to South Asia. Also, those new technologies, they're playing a key role. I think the molecular diagnostics, I think that's game-changing technology. But also the modeling work that's been done has taken us into completely new areas and really expanded our knowledge. And I think the artificial intelligence, remote sensing work are going to be increasingly important. I think clearly we're going to need, in the future, more multidisciplinary approaches to combat these increasing threats from transboundary diseases. And I think, rust is just one example of these. Just to finish off, just a huge thank you. I mean, a huge number of people have been involved in these efforts. I mean, a truly fantastic suite of donors that have supported the work, but then an equally impressive set of partners, different institutions all around the world, many different countries that have made all this work possible. So thank you very much.